So, hello everyone. Welcome to the third session of the second day of Limit Online Math Camp. Uh, today, Hrishik Koley. He did his BMath from ISI Bangalore and he is a math first year student now. He is interested in combinatorics probability. Uh, and today he will be presenting on a tale of two cities on some games actually. Uh, Over to you, Hrishik. You can start.
Thank you, Vikramda, for the introduction. So I'll just share my screen. So yeah, is my screen visible?
Yes, it's visible.
Yeah. Okay, thank you. Yeah. So as Vikramda said, I'm Rishik. I'm mainly interested in combinatorics. So I like to introduce some fun games that we try to study in combinatorics. Though I put it as games, but they are not actually games in itself. They have quite a bit of involved theory behind them. But let me just dive into it. So first, let's start with what is combinatorics. So combinatorics is the branch of mathematics that deals with counting, arrangements, patterns, structures.
Hrishik,
It's
hello.
very easy to, yeah.
Hrishik, sorry to interrupt.
Uh,
Okay. Actually, it was not visible just some seconds ago.
oh, okay. Yeah, if it's not visible, just let me know.
Yeah, now it's okay.
Yeah,
Continue. You can continue.
yeah, yeah. So it's pretty easy to ask the questions that combinatorics exposes. Unlike other fields of mathematics, it is pretty easy to explain them to anyone with little to no background of mathematics, but sometimes it can be very hard to answer these questions. Some common questions that it might ask is, well, assume there are five
Sorry to
people.
interrupt, Rishik.
Yeah,
The
yeah.
slide again went away. I think you can. You don't have to maximize the, or maybe you don't make it full screen. Then it will be visible.
Okay, yeah, maybe I'll reshare this. Wait a minute. Yeah, is it visible now?
Yeah, it's visible.
Yeah. Yeah. So, what's the kind of questions that we ask in combinatorics? Well, one question that you might have seen is assume there are five people. Everyone, each of them has one book. So, in how many ways can you redistribute these books among these five people such that no one gets the book that they had originally? A much easier question that you might have seen is, let's say you have three cities, uh, A, B, and C. So, let's say there are three paths from A to B. And let's say you have two paths from B to C. So how many ways are there that you can travel from A to C? Well, you have three choices of paths to travel from A to B. So we represent that by 3C1 and we call this 3 choose 1. And then they have two choices for traveling from B to C. So essentially 2C1. So it's basically the product of this, which would be 3 cross 2 equals 6. So you can just travel via path 1, then path 1, path 1, path 2, path 2, path 1, so on so forth. Now, a bit more involved questions that we might ask is uh, something like this. Let's say you have some rhombus shaped tiles. So what I mean by this is something like this. And you try to tile a hexagon using these. So you try to tile this shape using this shape tiles. So, like, how many ways are there to tile this entire hexagon using these rhombus shaped tiles such that no two tiles overlap? That's one question that you might ask. Or maybe you could ask, can you color the vertices of a graph using k many colors such that no two adjacent vertices are the same color? This, if you attended Devansh's graph theory tutorial last day, you might find this familiar because he tried to introduce the four color theorem and the ideas of five color theorem. So he tried to introduce coloring. So you might find this idea quite similar to that. Another question could be, let's say you have a set, say S, and it has, let's say, k many elements. So the cardinality of S is k. So, like, what is the minimum k such that I can choose n many elements from this very set S whose sum is equal to a multiple of n? So that is another question. So combinatorics is not just about, well, asking how many. It can also be a question with an yes or no answer. Or it could be a question that gives you a lower bound or an upper bound on things. Like a bound under which it works, but outside which the question does not quite make sense. So let me start with a very simple question to you all. So assume you have a staircase with 5 steps. So something like this. Yeah. So now you are allowed to take either one step or 2 steps at a time. Could you tell me how many ways are there in which you can climb the stairs? Anyone has an answer, they can tell. I'll wait for a minute. Okay, anyone has an answer? Does no one have an answer?
Yes, yes, sir.
Huh? What? Sorry.
Eight.
Oh, yeah. So there are 8 ways to climb the stairs. Yeah. So fun fact for you guys, that is exactly the 5th Fibonacci number. And you will see that if you increase the number of steps, let's say you take 6 steps, 7 steps, it corresponds with, like, you have n many steps, so it corresponds with the n plus 1th Fibonacci number. That's not something we'll delve into, but well, you can look it up. It's fun. So yeah, for a visual aid, you have these 8 ways to climb those 5 stairs. So moving on. So just like this very simple question, what today's talk will try to explore is very simple games like firing points from vertices or trying to tile floors and how they connect to very deep and beautiful mathematics. So as my title suggests, it's a tale of 2 cities. So I divided 2 simple games into a story of 2 cities. So starting with our first city, I call this the Kingdom of Graphonia. So in this land of Graphonia, there are cities connected by roads. So, and of course, if it's a kingdom, it must have a king. So the king of Graphonia now has a strange rule. This rule is called coin exchange. So the coin exchange rule states that whenever a city has enough gold coins to send one to each neighbor, it must do so. Well, kind of like, let's say you have one city here, and then let's say it's connected by roads to 4 other cities. And then this city is connected to 2 other cities yet. So let's say this city has 4 gold coins. Now, the number of gold coins that it has is enough to send one to each of its neighbors. So what it does, it sends one to each. So now this city has 0 coins and it has sent one to each neighbor. So earlier it had X coins, say. So now it has X plus 1 coins. This had, let's say, Y coins. This has now Y plus 1 coins. Let's say this had Z coins. This has now Z plus 1 coins. And let's say this had W coins. So now this has W plus 1 coins. Now, what could happen is this could potentially result in a chain of coin movements, sometimes which could potentially lead to utter chaos. So what I mean by that is, coming back to this example, after this vertex like donated coins to all of its neighbors, let's say if W was equals 2. So as soon as it got a coin from this city, now it has 3 coins and it is capable of donating 1 coin to each of its neighbors. So while earlier it was not, so let's now this has A plus 1 coins, this has B plus 1 coins, and this has again 1 coin. So earlier, this vertex with W coins was not able to donate coins to its neighbors because it just did not have enough gold coins. But now, after getting 1 coin from one of its neighboring cities, it just has enough and it donates coins to its neighbors. So this process could go on, right? Okay. So now, what we try to see here is what happens next. So now, as Devansh introduced the concept of graphs last day, I will assume that you remember the definitions of what are vertices, what are edges, and all that. What is a degree, what are neighbors of a vertex. But if by any chance you don't remember any of that, please feel free to ask. I'll just recall everything. So consider the cities to be the vertex in a graph and the roads between the cities to be edges. Now, it does not necessarily mean that every city has to be connected by a direct road to every other city. It could go via another city to a city. So yeah, the roads are the edges of the graph, and the points that each city has, we call them chips. So, well, this coin and kingdom setting is just to keep it more fun and engaging. But while in mathematics we call this the chip firing game. So yeah, that's where the chips come from. So the number of roads from each city is the degree of the corresponding vertex. And we have a rule called the firing rule for this chip firing game, which states that a city or a vertex can only fire if it has at least as many coins as neighbors, sending 1 coin to each. So if you remember what a degree of a vertex is, we denote it by dv. So if number of points on so if the number of points on the vertex v is greater than or equals to the degree of v, then it is allowed to fire, otherwise it's not. So let's get on into a more hands-on approach. Let's try an example. So consider this graph. Now, in this, let's say this is the initial configuration of the graph. So now let's name this vertices A, B, C, D, and E. Yeah. So now this vertex has 0 coins, so it is not eligible to fire. It does not like satisfy the conditions of the firing. Same D has 1 coin, so it does not satisfy the firing rule conditions. Same for C. But B satisfies the firing rule conditions. Same for E. E does too. So we have a choice what to choose. Like we could fire using this vertex B, or we could fire from this vertex E. So let's say I choose E to fire. So I fire from this vertex E. So the number of points it has reduces to 1, and the points on D and C become 2 and 1 respectively. Now we just have one choice of vertex to fire, that is B. So we fire from there, and it changes the number of points on its neighboring vertices. So mind you that in each step when we fire, it just changes the number of points for just itself and its neighbors. It does not affect the rest of the graph quite as well. And in the very next step, we again have just this choice of firing. So we can just fire from B. So we do that. Now we reach this step. Now you can check here that for all of A, B, C, D, and E, they do not satisfy the conditions of the firing rule. So we can no longer fire. And this is what we call a stable state. So as soon as you reach the stable state, you have no chance of firing anymore, so you stop. And that is our goal. So now let's make the story that we introduced a bit more complicated. Imagine now that there is a path to the main city from some of the other cities. So if there's a kingdom, there's a king, and if there's a king, there's a castle. So let's say the main city has the castle. Now, the main city or the city with the castle must be connected to the other cities of the kingdom, right? Because a kingdom is made up of many cities. So the main city is where the king lives, along with the nobles and also they must have some kind of privilege. So this king now has some rule called tax. This tax rule states that, well, all cities other than the main city must follow the coin exchange rule. That is, no matter how many coins the main city has, it never has to send coins to its neighbors. So earlier, for all other vertices, we had that if coin of vertex V is greater than equals degree of V, then we fire or donate. But now let me name this main city where the king lives as S. So the number of coin on S should ideally, by the coin exchange rule, also fire when it's greater than the degree. But this exception of tax gives it the liberty of not needing to fire. So now this very main city, or where the king lives, we call this city the sync vertex and we denote it with an S. Again, getting our hands dirty a bit and trying out an example. So this is our sync vertex, naming these cities B, C, D, and E. So again, we have two choices of firing, B and E. E fires the number of coins and C and D changes. Now the sync vertex comes into. So, okay, so one more thing is that we do not really need to keep a track of the number of coins the sync vertex has, right? Because if it does not need to fire, what's the use of keeping a track of the number of coins then? It does not matter whether it exceeds any threshold because it never fires, it just takes, it never gives. So yeah, now we have this choice that this B vertex fires and that's our only choice, so we make it fire. And so its number of coins reduces to 2. One of its neighboring vertex now has 3 coins. And one of the coins goes to sync vertex, but doesn't really matter. Next step, we so next step, it fires from here. It has 2 coins here. It again fires. One of them goes to the sync vertex, one of them goes to the other neighbor. And the sync vertex does not really care, so we move on. And then I fire from here. One of them comes to the sync vertex, the others are redistributed to the other 3 vertices. So we again reach a stable state. But now we need to understand this. Why is this sync vertex important? So to understand that, I need to introduce some special ideas, special rules. So one of the rules, or rather than rules, it's basically our goal. So our goal is stabilization. Always was, always will be. We want to reach a state where no vertex can fire, be it with the sync vertex or without the sync vertex. Because otherwise, if we have a choice of firing, then we will continue that process, right? And the second rule is that I think that the graph we are considering has no sync vertex. And now we continue this firing process till we attain stabilization. So the total number of chips in the graph stays constant throughout the firing process. Like take any instant, say after n number of firings from in the graph, you want to count the number of coins that are present in the graph right now. So that will be same as the number of coins it had at the very beginning. So to see that, yeah, so you can check that we started from here. We had 8 coins. The next step, we again have 8 coins. The very next step, 8 coins. And even after we reach the stable state, we have 8 coins. But that's not the case for the sync vertex. For the sync vertex, we started off with 7 coins. We started off with 7 coins. The next step, we do have 7 coins because no coin goes to the sync vertex. But now coins are slowly starting to go into the sync vertex. So the number of coins decreases. We have 6 coins here, 5 coins here, and by the time we reach the stable state, we just have 4 coins. So now I come back to my question is why is the sync vertex necessary? Well, it is necessary because you can check this that if the total number of coins in the graph is greater than equals yeah, if the total number of coins in the graph is greater than the summation of the degree of all vertices minus 1, then this firing process will never stop and we will never reach a stable state. So in case you don't know, this VG is called the vertex set of the graph. It is basically all the vertices that are present in a graph. So yeah, let's consider for this graph. So the degree of E is 2, the degree of C is 4, the degree of B is 2, for A it's 3, for D it's 3. So now if the number of coins is less than equals this, then we can hope to reach a stable state, right? But so for this number would be equal to what? 3, 4, 5, 6, 7, 8, 9. Yeah. So for this, the coins must be less than equals to 9 for us to hope that it will at some time reach the stable state. So now I assume that there are, let's say, 10 coins in the graph. So the best you can try to do is assign coins to vertices such that it is less than its degree. So let's say I assign 2 coins here. Let's say I assign 2 coins here. I assign 1 coin here. I assign 3 coins here, 2 coins. So now I have used up 8 coins and I am left with 2 coins. So I must assign the remaining 2 coins here to satisfy the condition that I imposed on the graph that the coins are equals to 10. So now you will see that at any, no matter how many times you have fired this any vertex, you will always have a state where firing is possible. Or to put it simply, there does not exist any stable state for us to reach as the number of coins remains conserved throughout the firing process. So that is why the sync vertex is necessary, because sync vertex relaxes this condition that the number of coins must be lesser than this set number. Because even if we have like this many coins, even if you have more than this many coins, then the sync vertex takes away some coins from the system and allows it to stabilize after a while. So now let me show you a simulation that would help you to imagine this. So I'll stop sharing the screen for once and then I'll share it again. Yeah, so is this visible?
Yes, it's
Okay, yeah. So now consider this. Yeah. So now there are roughly, so consider each of the small square cells as a city. So now there are roughly 10,000 cities or 10,000 vertices in here. And we say that if one of the square cell, if 2 square cells share a side, then they have an edge in between. So potentially for square cell could donate to all of those squares that it shares a side with. So now I introduce points in this system. So to keep it simple, I'll just assign equal number of points to each of these vertices. Okay, one more thing is, as soon as point, sorry, a vertex fires, that so as soon as a vertex on the boundary fires, it sends points to its neighbors, but also to this whole black region outside. And this entire black region is basically a sink. Let's just go by that. So yeah, I start adding the points in here. So this website is kind of color coded. So white means there are no coins. This light gray is there's one coin on each vertex. This darker shade, 2 coins. This here is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So maybe 13. Okay. So now each of these small square cells has 13 coins each. So now I start the, so okay, you see this reset counter button here. There is a number beside it, 0. So that keeps a count of the number of firings required for it to reach a stable state. So as soon as I press play, it starts the firing process, and it kind of beautifully goes on about this firing process as long as it does not attain stability. So let's start that. So yeah, you could possibly see that it gives rise to very beautiful patterns. Now, this is not something that this is something that ties to the mathematics beautifully, but more so because this has this beautiful symmetric harmony. That is one more thing that I included this for, just to make it visually more appealing. But well, moving on from that, I'll share my slides again. Yeah. So now another idea that I want to introduce is a very important property that enables us to study this chip firing game, is that at any point during the firing process, we may have more than one vertex that have more coins than its degree. So going back to this, yeah. So in the very first step, we had the option of either firing from vertex E or from vertex B. So if we have such an option, then no matter what order we follow to fire these vertices, we always get the same result, that is the same configuration at the end. So the entire process from going from the initial configuration to the stable state configuration, no matter what order we fire the vertices in, we'll always get the same stable state configuration. And we call this the abelian property. So if we want to try this out, let's go back to the slide. Yeah. So let us say we start firing from this vertex with 4 coins. So if we do that, we get something like this. This has 3 coins. This has 1 coin. This has 1. This will have 2. This will have 1. And then if we choose to fire from this vertex with 3 coins, then this will now have 1 coin. This will now have 2 coins. So this will have 2 coins. And then again, if we only have the option of firing from this very vertex. So this had 2 coins earlier, now it has 0 coins after firing. This gets 3 coins and this gets 2 coins. So you see, this is the same state as this stable state. So now what if we try to prove this formally? Now I hope all of you are familiar with what induction is. So I'll assume that you know. Yeah. So using the very simple induction idea, and I of course assume that the firing sequence eventually ends or stabilizes. So the base case would be that we have two vertices that we can fire, and the result after firing both is independent of the order because coin movement is local and conservative. So conservative is the same idea that the number of coins throughout the process, if no single vertex is involved, is conserved. But what do you mean by local? So you have some vertices. Let's say you have this graph, or maybe this. Yeah. So maybe you fire from this vertex A. So firing from vertex A only affects the vertex A itself and the neighbors of A. I denote that by NA. So what are its neighbors? Its neighbors are these vertices B and C. So the count of the coins that can be changed by a firing from A are just these three vertices A, B, and C. And the rest of the vertices, say this D and E, or maybe if we had just more vertices in here, all of those, the coin count on all of those remain unchanged. It does not affect them at all. So that is what we mean by local. And now let's say we do a firing from this vertex A and this vertex C. So that changes the coin count on this AC and on the vertices B and E. So if you have a set of vertices that you conduct the firing process from, then it just affects, let's say I call this set S, then it just affects the coin count on the vertices in S and the neighbors of the vertices in S. That's what I mean by the firing being low. And okay, yeah. Another thing would be, let's say you have two vertices, A and B. So let's say they are connected to some vertices. Now, let's say you start firing from A and then go to B. So firing from A increases the number of coins on this by 1 and leaves all other vertices that it's not connected to as it is. And then I move on to B and it increases the count of all its neighboring vertices by 1. And so essentially and if I do the same, like firing from B at first and then from A, it gives us the same configuration. How so? Because if a vertex is just connected to A, then it's like coin count is increased by 1. Or if it's just connected to B, then its coin count is increased by 1. If it's connected to both A and B, then no matter if I fire A first or B first, its coin count will always be increased by 2. That is the basic idea that you can use to show that, well, you have two vertices that you can fire. The result after firing both is independent of the order because the number of coins remains conserved and the coin movement is local. Now you can use the induction hypothesis for n-1 vertices and extend it to n vertices. And classic induction conclusion gives you that the abelian property holds. So we call this the abelian property. So yeah, now I have a question for you. Can you construct a graph and assign coins to each vertex for which the firing process never stops? But I'll like to impose some conditions. First, graph has no single vertex. And my second condition would be, well, you are smart people, so you can always answer me that, well, the number of coins I keep in the graph would be greater than this number. And now I will have an infinite firing process, a firing process that never stops. So I constrained you to this, that the total number of coins on the graph must be less than this number, less than or equals to this number. So I don't want an answer just now. Maybe I'll move on to the next section, and at the end of the talk, we'll come back to this. For the time being, you could have a thought, and then if you come up with an answer, we can discuss it at the end. But what do we study in this chip firing game? Like, I introduced the game to you. So what we study is algorithms which we could use to answer such which we could use to reach a stable state given an initial configuration, or some ideas from algebra that helps us to understand if a given configuration is at all I is at all does it at all have a stable state that it can reach at some point after some finite number of firings? These are all questions that we try to answer in the chip firing. It relates to some much deeper ideas too, but well, if you ever try to pursue mathematics as a career, maybe you will get introduced to those ideas. It will be fun, I believe. But okay, so let's move on from it. Let's move on to our next city. I call this the city of Thessalacia. So imagine there's a temple. So now at the middle of the temple, so the temple has a cement floor, and in the middle of the temple there is a 4x4 block that is made up of marble, let's say. And you have dominoes, that is 2x1 rectangle tiles, which is used to cover this 4x4 blocks. So a domino is basically this shape. Any orientation works. We call it a domino. So now one fine morning, a mischievous magician comes to this temple of Thessalacia. He does not like these domino tiles. He gets furious, and what he does is he magically removes a 1x1 square from the corner. So earlier you had this 4x4 piece in the middle of the temple. He just comes in and removes this 1 square from the side. Now you are left with this remaining shape. But that is not the only thing that he does. Because, well, that makes the job easier for people, right? Because if he removes this one block, you could just remove another block, and then it is again tileable using those same dominoes. So what he does is he makes it harder for them, and he converts all those domino tiles into L-shaped ones. So now our goal or our question is, can we tile this new shape that we are left with using this L-shaped tile? So what are these L-shaped tiles again? So L-shaped tiles look something like this. So this is a L-shaped tile. So my drawing is not that good, so I'll give you a better visual aid. So yeah, this is a domino tile on my left, and on the right of the screen, that's an L-shaped tile. And these are the previous grid that I had, and this is the new one after the corner square missing. So now maybe earlier this shape was this full 4x4 grid was tiled using domino tiles. So maybe it was tiled something like this, something like this. And now it can be tiled in this way. But a bigger question that might come to mind is, what if I did not have a 4x4 grid? What if I had an 8x8 grid? One. Two. The another question that might come to mind is, what if I did not remove a corner square? What if I removed a square from somewhere in the middle? Let's say, let me go back to the last slide. Yeah, maybe let's say I remove this square. What would happen? Well, I'll try to answer both of these questions at once. So consider this 8x8 grid, and consider this blacked out cell as the one that has been removed. So now what you can try is put an L-shaped tile here. And now divide this entire 8x8 grid into 4 parts. Now, you can think of this as basically four 4x4 grids with one corner square missing in each. So now you already know how to tile a 4x4 grid using L tiles. And so you can tile each of these uh, 4x4 grids with one corner square missing pretty easily. And the tiling would look something like this. So the more general question would be to ask, if I have a 2 to the power n cross 2 to the power n board with one cross one square missing from somewhere in there, can we tile this using L-shaped tiles? The answer is obviously yes, but the question is how. So for a 2x2 case, 2x2 grid, if one tile is missing, you have that L tile. For a 4x4 grid, you divide into 2x2 squares and then you tile it. And for the very general case of 2n cross 2n, you divide it into 4 quadrants, each of 2n minus 1 cross 2n minus 1. Same here, same here, same here. So one of the tiles is missing in one of those quadrants. Let's say this. So for the rest of the 3 quadrants, I place an L tile here. Now I can think of each of these as a 2n minus 1 cross 2n minus 1 grid with a corner tile missing. Now use an inductive idea. Use the same type of induction that with the corner square missing, I know how to tile this. So I am done with this, this, and this. I come to this 2n minus 1 cross 2n minus 1. So the general inductive idea would be to consider this, that for n equals 1, that is 2 cross 2 grid, I know how to tile this. So our induction hypothesis is, given any 2 to the power n cross 2 to the power n grid with any square missing from in there, I can tile it using L tiles. Now, what if we have a 2 to the power n plus 1 cross 2 to the power n plus 1 grid with a square missing from somewhere, divided into 4 quadrants, and now you have and place an L tile in the center. So now you have basically 4 different grades of size 2 to the power n cross 2 to the power n with one missing square somewhere in there. And by your induction hypothesis, you can claim that, well, this is tileable using L tiles. And thus you get that any 2 to the power n cross 2 to the power n grid with a square missing from anywhere in there is tileable using L tiles. So my question again, what happens if more than one square is missing? Can we still tile it using L-shaped tiles? Before thinking about that, let's go back to our chip adding game and let's try to answer that. Okay, yeah. So did you think about this? Do you have some idea about what kind of a graph fits this? Or maybe you may think that there exists no such graph. So if you have any answers, chat, or you could just say. Oh, okay. So I am to re-explain the question that basically, can you construct a graph and assign points to each vertex such that the firing process never stops, provided the graph has no sinc vertex and the number of coins is less than equals summation degree of v minus 1. Yeah, when do you get an infinite loop? So could you give me an example? Okay, let me also clarify this, that I'm not an infinite graph is an example of this, but let's say we constrained ourselves to a finite graph, that is a finite number of vertices. So can you give an example for that? Like you have an idea. Sorry, Aditya, I did not get your point. Could you like explain? Okay, maybe I'll give you the example of what this. Okay, yeah, sure, man. Go ahead. It's like a four dimension that not have a time.
That already means the infinite graph, right?
Yeah, what I'm talking about is a very simple graph, like finite number of vertices, finite number of edges, everything else finite, finite number of coins. Okay, let me give you the example.
Can I
So,
try?
uh, yeah, sure.
Just take one edge, and at the two end, put 0 at one end, 1 at one end.
Yeah, this one works. So this creates a infinite number of firings at any point. Or maybe this graph also you could try. This one was the one that I had in mind. So you could
Yeah, maybe
assign.
I thought of too simple one. Okay.
Wait, sorry, how is like the degree over there? The degree is like the summation of degree v minus one. That is not satisfying. In the zero one, right?
Yeah, there are 0 coins here, 2 coins here, and 1 coin here, right?
No, what is the edge with zero and one on the vertices?
Sorry, I don't get it. So the
Like
coins
there,
are on the vertices. It's not on the edges.
yeah, but there's an edge drawn with zero and one on the vertices. That does not satisfy coins is lesser than or equal to the summation of degree v minus one.
No, that does, right? Because the number of coins in this graph is 1. And oh, okay, sorry, my bad. Yeah, that does not satisfy.
Oh,
Sorry, I
sorry.
did not get a look at it. Yeah, sorry.
Then your example works. Tell
Uh,
me.
yeah, so A has degree 2, B has degree 2, C has degree 2. So this value for this graph becomes 3. And then A has 2 coins, B has 1 coin, C has 0 coins. So the number of coins is equals to 3. So this condition is satisfied and I do not have any sync vertex. So if I fire, this goes to 2 coins on B, 0 coins on A, 1 coin on C. This goes to 1 coin on A, 2 coins on C, and 0 coins on B. And this goes to this. And this chain continues. So now I would like to tell you a idea that's very core to mathematics or many other fields. For example, that is an if and only if condition, or what we in mathematics call necessary and sufficient conditions. So now, as I had introduced that this condition, like if I have a graph with no sync vertices, then this condition was necessary for us to reach stability. But as you can see that we have this example where we do not reach stability even after we have satisfied this condition. So that is what we mean by sufficient. Like A happens, A happens if B holds. Sorry, A happens only if B holds, but doesn't mean if B holds then A must happen. So the converse may not be true. So this is a necessary condition for a graph to attain stability, but this is not a sufficient condition. So Coming back to this question, could you tell me what's the necessary condition for tiling any shape using L-shape tiles?
I mean, unnecessary thing is like just mod 3, but that is
Yeah.
not sufficient.
Yeah, that is not sufficient. Could you give me an example why it's not sufficient? Like where it's not sufficient?
I mean, no, it might be, but I'm just saying it. We don't know if it's sufficient or not.
Yeah, okay. So that's true that if it's 0 mod 3, then this is a necessary condition, but it is not sufficient. I'll give you a counter example for that. So this, I take out these tiles and these tiles, the squares. So now this new shape that comes up is the number of squares is divisible by 3. So 1, 2, 3, yeah, 12. So it's divisible by 3. But this is not really tileable using L tiles. The easiest way to see this is that you see cannot really place any tile that covers this particular square, because like there is no place to place an L tile here. So
Can I tell?
go ahead. Yeah, go ahead.
You make a square of 8 gates, 8 by 8.
8 by 8. Okay, that will take a bit of time. Does it have 1, 2, 3, 4, 5, 6, 7, 8? Yeah. 1, 2, 3. Yeah, you know what? This is too much work. Just let me go to some of those pictures. Yeah, go ahead. I'll just explain it at this. Yeah, it was like that.
Then place out 6 middle tiles.
6 middle tiles.
Yes.
Could you tell me the places where I should place it? Like
The
here?
third. Yes. And
Okay,
yes.
cool. Yeah.
And
Then-
the side. That. 3.
Here,
No.
like this.
Here.
Okay. So this would
It could be.
then. Okay. Let me check. Is this? I can tile this. I can tile this. Can still tile this. I can tile it using L tiles. Wait, let me just remove these lines and tell you how. Yeah, so you said I place this and this. Like I remove these and these. Wait, is this removed or is this not?
It is not removed.
Okay. Yeah, so then this does not satisfy the mod 3 condition itself, right? Because in itself it has 64 minus 6. So how much is that? 58. Yeah. 58 cells. So it does not satisfy the like sufficient necessary condition. So it like it is not tileable that much we. Yeah, so basically my point is it's not really necessary. If a condition is necessary, it should be sufficient. But Well, now the type of questions that we study in tilings. There are questions like how many ways you can, like, for example, you saw this. What? Yeah. Yeah, you saw this tiling of the 4x4 grid. So one common question is using these dominoes, how many ways are there to tile any M-cross-N rectangle? Because this is clearly not the only way to tile this 4x4 grid. I could have just done the tiling in something like this, this. This is also a tiling, and this is different tiling than the one showed on the next slide. So yeah, there could be more than one tiling that is possible using a particular shape. So that is one type of question that we try to study in tilings. Another kind of question that we, we deal with various shapes and various kind of types. Another kind of question that gets much more involved is, well, now we are trying, what we are doing here is doing everything on 2D. So sometimes we move on to 3D and 4D. Okay, not 4D. It's just 4D. Yeah, sometimes we move on to 3D shape and then we call these brick tilings. Like then the tiles have height, breadth, and length, all of these dimensions. So we consider tilings there. And then we study some very interesting phenomena in tiling. Like, for example, the question I asked at the very beginning, like if I use a rhombus to tile a hexagon, how many ways are there? But a more famous phenomenon that we study in rhombuses, it's called the Arctic Circle phenomenon. Not very easy to like prove, but pretty easy to state, as I said. Things in combinatorics are easier to state than to prove. So yeah. Now you can have an intuitive idea is that I'll just draw a bigger one maybe. So let's say you have this big hexagon and you use these rhombuses to tile it. So now at this corner, you can notice that the only shape that you can use to tile it is this rhombus. And then you have this. So what the Arctic Circle phenomenon basically says is that around this corner regions, if you, so you got the idea of probability. So there was a term that has been used time and time again in all of the probability tutorials or anything that related to probability, that is random. So random means I try to place tiles here randomly without any particular order, provided the tiling is like suitable or acceptable, that is there are no overlapping tiles. The tiling around these corner regions will always be the same. That is called the Arctic Circle phenomenon. So these are some things that we try to study in combinatorics. These are some particular ideas. So moving on, combinatorics uses very clever counting arguments sometimes to answer some extremely complicated looking questions, though easy to state, or sometimes it uses very algebraic conditions, probabilistic conditions, number theoretic conditions to answer very easy questions. So what might look like a game might become deep mathematics, and combinatorics shows us that patterns, puzzles, and proofs can all begin with play. So yeah, that's all for my talk. If you have any questions, any doubts, please feel free to ask. Yes, please. You can just speak up.
So what are like the applications of the chip firing game? Any real world examples where we can use it? in mathematics?
Well, well, in mathematics, it's studied very abstractly, but I could give you an example. That example is used in combination with another idea that is called parking functions. So let me just give a one-line answer to this parking function thing. So assume you have n many cars and n many parking spots. So now each driver has a favorite parking spot, and it is quite possible that like the best way to go about it is if every driver has a different favorite parking spot, but that's not always the case. Like if there are one, two, two, and so let's say 3 or 4 drivers could have this 2 spot as their favorite parking spot. So what happens is every car comes in and parks in their favorite parking spot. So if the ith car comes in and its favorite parking spot is J, it parks its car at the jth parking spot if it's empty. If it's not empty, then it moves on and parks at any of the parking spots that's empty between j plus 1 to n. So that's basically the idea of parking. So combining this idea of parking functions and chip firing, you can think of this. Okay, could you tell me which grade are you in? Like which class are you in?
11th.
Oh, okay, then it's fine. Yeah, so then you can think of something like an isolated system where there are atoms in there. So now you might notice that for any reaction to happen, these atoms share some amount of energy with other atoms. So now this parking function idea is used to keep a track of the like desired amount of energy. So the parking spot corresponds to the desired amount of energy. And these atoms are the cars in here. So using this parking function idea to keep track of the desired amount of energy, it basically uses this chip firing rules. And like as soon as it has excess amount of energy, it donates energy to all of its neighbors or the electron or the atoms that are colliding with it. So these are some places that it's used. And as it's an isolated system, it can't really dissipate energy to the surroundings. So all the energy remains trapped in this isolated system. So at some point, so basically there's no sync vertex. So it must at some point reach a stable states. And the goal for this atoms in the isolated space is also that very stability. So this is somewhere this chip firing and this new idea of parking functions, these are used. So basically stability of some complex systems is kind of studied using this chip firing and parking function. Does that make sense?
Yeah, nice.
Yeah, any more questions? Yeah, no,
Any
bro.
kind
There's
of
some
test?
kind of
No, no.
test. Yeah, you can just speak up. You don't need to raise your hands.
Sir, can we do this if the tiling thing? Can we do it if there is some other sort of shape of the tiles, like
Yeah,
not
sure.
L?
Like, what kind of tile do you want? Like, of course, there it needs to satisfy some conditions for the tiling to happen. Also, one more thing, please know, sir, I am not that older. You can call me Hrishik or Hrishik, that works. Yeah, so yeah, it basically depends that what kind of a shape and what kind of a tile you have. Well, given certain conditions, every shape is tileable with every other shape if it satisfies those conditions. You could try it out with other shapes. I showed you a hexagon. There are other shapes that are commonly studied like honeycombs. Honeycombs are something like this.
Mm,
I regret that I'm bad at trying.
yeah.
Yeah, so these hexagons, put together in a trash in the shape of a triangle. So those are called honeycombs. So these are some common shapes that you study, but you can try tiling on any shape that you. Yeah, yeah. Any more questions?
Can we use other shape?
Yeah, you can use other shapes. Like as I said, if it satisfies some particular conditions, you can tile any shape with any tile. Uh, of course, the conditions depend upon the tile and the shape given to you.
Can we, if the condition apply, can we use cycle tensor?
Sorry, what?
If a condition is like we have to make a um, anything condition, can we apply a cycle tile?
Yeah, like, well, if you have a rectangle, you can't really tile it with a circle, right? Because you will be leaving out some space on the corners and all. But let's say you have some shape like this. What is the a different page? This page is like a-
Or maybe I can
Yeah,
add
let's
something.
say, yeah,
So when you try to these ideas that you are filling some object with circle, filling some rectangle or square, this goes to it goes. Maybe you can think of it like what is the maximum number of circle that you can put inside a square, which, so that offers maximum takes maximum area. Maybe you can think of it like when you go to shop, uh, you can see an optimal way of putting cabbage or some kind of balls, so that you can put maximum number of them in a is as occupying as small volume as possible. This idea goes to a problem called sphere packing, and there are a lot of deep, interesting mathematics in this. Maybe you can look it up. Uh, I guess 2 years ago, some women got Fields Medal for solving some sphere packing problem. So yeah,
okay, yeah, Aditya, which class? Who asked this question by the way? Because I
yeah.
yeah. So
Yes,
Aditya, which class are you in?
I
Yeah.
8.
Yeah. So when you go to like 11th or 12th grade, you will have like if you take up science, then you will have something called solid state in chemistry. So that introduces some of these sphere packing ideas that Vikram spoke of. Uh, and you could like get an idea of what it looks like, but then these styling stuff comes in and this sphere packing stuff comes into mathematics and that explains this most in a much more robust and rigorous way. So as you were telling of circles, you could maybe have some shape like this. You can tile this using circles, right?
But then we will not call it tiling. We will call it packing.
Yeah.
Tiling means just occupies all the area.
The entire
Whatever
space,
is
yeah.
there. Yeah, that's fixed. And when you are putting circles or
Maybe
spheres,
you can look
we
at
call it
sphere
packing.
pattern as like just changing the shape that is to be tiled, right? Like this idea comes from that very idea that was talking is given a hexagon and then you put the hexagon end to end in the shape of a triangle. So instead of hexagon, you just use circles. Don't really cover the entire space, but well, you have just changed the shape to be tiled now. Yeah, so any more questions? Anything? Yeah, you can just
Guys,
ask. Don't raise your hands.
Yeah, so like you just stated the parking function, right?
Yeah.
So like how do you evaluate that for any given n?
Uh, that like evaluating that goes into some bit of rigorous like arguments. I don't think I have enough time to get into that, but you can like just Google it up and you will. So you can just Google up parking functions and you will get some ideas about how to compute it around and like other.
Okay, thanks.
Yeah. So and if you want to look at some other like interesting ideas in combinatorics, one book that does it very well, I believe, is this one. So, third, yes, stadium. The art mathematics. This is by Bolovas. So yeah, if you want similar ideas about tilings, then similar ideas in combinatorics, then you can look at this book. This is a great. Yeah. Anything else? Any more question? Feel free to ask.
Is there like some kind of definite method of approach for tackling a problem in combinatorics, or just like it's extremely varied? Like, I can try some definite method. Is there a way to like in a definite way?
No, there's no like definite way to tackle a problem in mathematics. Like, sorry, in combinatorics, it used some different ideas. Like, not everything well fits a certain recipe. You have to come up with some argument to tackle it. There's no one way fits all problems kind of stuff to. Yeah, anything else? Wait, someone ask something in the chat. Yeah,
we can wait for 1 or 2 more minutes then. If
yeah.
there are no more questions.
I don't really know any good Vedic maths book for class 8.
The big math books, I guess. I think you can just Google it up and you can get very, very good
Yeah,
sources. Yeah. Very well established topic.
maybe I'll stop sharing my screen.
So, any more question? So, we can stop now. Thank you everyone for joining. Thank you, Hrishik, for such a great talk.
Thank you.
See you tomorrow.
Thank you.
Yeah, got it.